I always love seeing an expert turned coach who's happy to share information as well as inspire us into becoming better leaders as well as making better technical decisions as well. Our next speaker, I was going to hone in on my rapping skills as Slim Shady, but then I remembered that I really am just an MC, and that's a dream that I will not accomplish, but sure, look, it is what it is. But yes, Mihai Criveti is back once again, gracing our ShipperCon stage with these golden nuggets about building scalable GenAI Retrieval Augmented Generation platforms. I had to write that down because I was like, I will not remember that. Okay. With Kubernetes, LangChain, HuggingFace, and vector DBs. Mihai is truly the go-to guy for complex solutions and customer requirements. A senior technical staff member for Cloud Native and Red Hat Solution at IBM Cloud Solutioning Center. Accolades as long as my arms, and both arms, because I've got one short one, but accolades as long as my arm, as well as being referred to as a rock star. I would love it if you guys could give Mihai a huge ShipperCon welcome onto the platform today.
Thank you for the introduction. It's great to be back. Let me just share a couple of lessons from the experience I've had in building large language models over the last couple of months. And I must say, it's quite a painful experience. Anyone that's worried about AI replacing you at your jobs, we're not quite there yet. So what's a large language model? Well, the best way to think of a large language model, and slides are going a bit fast here, if we can go back to the previous slides. Oh. Must be AI. So let's try that again. All right. All right. Best way to think of a large language model is like a mathematical function. What's going on here, guys? 1 second. Is there a manual override for this thing? Not even touching it. Could you help me a bit? This thing is broken. So while we fix that, let me just explain what a large language model is. It's a mathematical function. It takes in one input, it generates one output. The input has to be string, the output is going to be string. So it's a text generation mechanism. Now, the problem with that is that you have a token limit of the total input and output size of the generation model. So let's say that you want to process a document. I want to use a large language model to summarize a 400-page document. Can you do it? Not really, because the token limit for most of these models is about 4,096 tokens. That's about 3,000 words, about 7 pages. So at any point in time, the memory, the working memory, the context of a large language model is about 7 pages. There are some models which have larger token limits, but generally they perform not as well, and they tend to be quite slow. So how do we overcome some of these limitations? Well, first thing you need to remember is that a large language model really is a one-way function. It doesn't do anything else. It doesn't have a memory. It doesn't remember. It doesn't learn from the experience. It doesn't work with your data. It's really like a function in Python or Bash where you define it, and the inputs are the text that you give it and the data that is previously seen. If it wasn't trained on your data, then it won't be able to generate the result that you want it to generate. That's not necessarily a problem. The problem is that if it can't generate the result based on data it's seen, it will make something up. So it will completely hallucinate. So one way to get around some of these limitations is to implement a pattern called Retrieval Augmented Generation, where you are injecting the data in real time in your prompts to the large language model from a database, from a vector database, from a document. Let's see if we can actually see which one is previous. Back. And which one is next? Okay, so it's fixed. No, I'm still not touching it. All right, let's see if we can go really, really fast here. So this is a large language model. So does anyone know what that is? This. That's, what is it? It's a modem. That's a US Robotics V92 fax modem with a serial port connection, which works on Linux. So back in 1995, if you had one of these, you were fine. You could run it on Linux, which was awesome, because it didn't have the self-modem drivers. Now, I want you to think of a large language model as one of these, right? But not that. 50 times slower than that. So this thing is fast. You could sit on IRC. You could have conversations with hundreds of people simultaneously on a modem. You can't do that with a large language model. In fact, an LLM will generate anywhere between 10 and 100 tokens a second. So token, 3/4 of a word. So it's about the speed of somebody typing, actually a bit slower. So how expensive is that? Well, if you really want to run the latest open source model, like Llama version 2, you need about 78 gigabytes of video memory for that performance, which is about $20K a month on AWS. So you're paying $20K a month for somebody that's as fast as somebody typing on a teletype. Not exactly ideal in terms of performance. There's also latency, the time to first token. So whenever you type, the model will think before it's able to give you some text back. So to overcome some of these limitations, we've introduced a pattern called Retrieval Augmented Generation, where you're not actually talking to the model the first time. What you're doing is you're taking all of the data that you want the model to interact with, your databases, your files, your PDF documents, and you're throwing them into a database. Now, instead of using something like, I don't know, PostgreSQL, we're using a vector database for a very simple reason. If you want to search for something in SQL, you say select star from users where name equals something, right? But the name has to match. With a vector database, it doesn't have to match. So for example, if I want to search for sky, I can search for blue, and it will find sky, because those words are related in vector space. So by doing a search first in a vector database, we're able to get results of near word or near vectors from that and inject them into our prompt. So we're working with about 7 pages of prompt in our context window, and we're literally telling the model, with the following information, which represents an extract from business documents, I want you to summarize the results. Then you give it the chunks, usually 10, 15 chunks, which fit within that context window. And the model will now generate the results based on your data, like the top 10 chunks, and the data it has previously seen. So it's a mechanism for you to engage an LLM with a vector database with data that is previously seen. It's a way to accelerate some of these results. And if you're smart in the way that you're returning results back to your user, so you might return first the vector search information, then you might do streaming of the content that you get back from your LLM. You're implementing a asynchronous API, and you're multiprocessing across multiple GPUs. You might be able to get decent performance out of your LLM. So here's a couple of tricks that I like to use. Well, slides keep moving. One of them is caching. So you want to cache the results from your large language model. I know this thing is quite effective. You're going to find the full deck and presentation available on my YouTube channel. So search for Criveti Mihai. You'll find the 30-minute version of this talk. I promise you the slides don't move by themselves. They move a lot slower. But if you're interested in building applications with large language models that scale, if you want to understand some of the limitations of these LLMs, the best advice I could give you is to pick up Jupyter Notebook, LangChain, and ChromaDB, and build an application that interacts with your document and lets you have a conversation with your document. The way that works is, well, quite simple. remember, an LLM doesn't understand anything but text. A PDF is not text. It's a binary file. So first you need to convert that PDF to text. Great. Let's say that our starting document is a Form 10K, which is something that companies submit at the end of the year, presenting their financial information. And I'm going to put a company there. Let's say ShipItCon is a company, right? It has a Form 10K. It's a 300-page document. It explains the locations from where this company operates. It's very useful information. And I want to ask the large language model, what are the countries where ShipItCon operates in? Or what kind of business does it do? Is it profitable? What are the top products? So these are example questions. I want to have a conversation with this PDF document. Well, no matter what large language model I choose, it probably hasn't seen any of that data. So I'm going to either train a model, which is going to cost a couple of million, depending on how many GPUs I need, or I'm just going to insert chunks from this Form 10K in real time in my prompts. That's the second approach we're choosing. It's called Retrieval Augmented Generation. So we take the PDF, we convert it into text. We can use LangChain for it, or Python libraries that convert PDF. But remember, this is an imperfect process. When you convert PDF to text, what happens to your images? Embedded videos. What happens to tables? Because they don't get converted nicely. Do you need to do OCR on the PDF? What happens to comments? Metadata. When the document was uploaded, all that information is information that you need to think about in the process of designing your application and use it to enhance the data with metadata. Like the previous talk, all data is data. When was the file edited? Who was the file created by? Now we have a 300-page text document. It's been converted nicely. But we can't just throw it into a large language model for a number of reasons. First, it doesn't fit in my 7 pages context window token limit size. Second, if I were to give it, so there are some models like Anthropic Claude, for example, that has a 100K context window, it's going to be very, very slow. And it's going to generate usually garbage if you give it too much data. So I'm going to take that document and I'm going to chunk it. Chunk it basically means I'm going to split that document into smaller, usually about 300-word chunks that overlap a bit. And I'm going to enhance them with some content. Let me try my luck here to see if I can actually get a diagram of how that looks like. Let's not touch it. So once that I've chunked this information, I'm going to vectorize it. So I'm going to use a model. In this case, what I'm using is SentenceTransformers models. You can find these on HuggingFace or in Python, which turns a bit of text into a vector representation of that text. And that's also an expensive process. It's not as slow as using an LLM, but it is still an expensive process, so GPU acceleration can help. Now that I have those chunks in vector form, I'm going to load them into Weaviate or ChromaDB or any of these vector databases. And I'm also going to vectorize the question. So the question could be, what are the countries where ShipItCon operates? In the document, somewhere says Ireland, perfect. I vectorize the question using the same algorithm. I vectorize the document, and now I can do a vector search. But I don't have to ask what are the countries. I can ask where. I can ask where's ShipItCon? Because it uses vector search, it will find that information in my document. It will feed the top 10 results into the next step. And I can either re-rank those, enhance them with a bit of metadata, and feed them to my large language model. So what do I do with this in the LLM? Well, I might want to do a question and answer or a summarization of that. So I can say, using the following input, try to answer the question truthfully. Say, I don't know if you don't know. So you craft the prompt a little bit. You give it the prompt. You might even say summary at the end or response at the end, because the model works based on prediction. It's literally your iPhone's autocomplete on steroids. So when you use autocomplete on your phone, it will complete the next word based on the previous word. An LLM will autocomplete the next word based on everything else that is seen, including the prompt, which is often invisible. ChatGPT and other similar large language models simulate cognition by crafting the prompts. So for example, it simulates a memory by injecting what it's previously seen in the next prompt in a moving context window. But it doesn't remember, it doesn't learn from your experience, right? So you're always crafting this prompt. And now we have our document, we have it in a vector database along with hundreds of thousands of other such documents. We're going to search for them, we're going to retrieve them, we're going to send them to the LLM, and now we're going to get back our results. You can apply the same kind of techniques for code bases. So I'm sure all of you have used AI to write code. And what you'll often see is if you give it a very simple problem, I want you to generate a function that adds two numbers together. You typically get decent results. But the more you talk to it, the dumber it gets. And you can't give it your whole code base. Say, here's my GitHub repository. I want you to refactor this code. Well, folks are starting to craft such applications using exactly these techniques. So they take the code, they feed it into a database, they first search for bits of the code, they give it to the model sequentially. Because if you were to give it your entire code base, it might take 50 hours to come back with a response. It's going to cost $200 a question, and the results you get back are going to be very unpredictable. So it's important to use these kind of techniques to accelerate it. A couple of other things to consider is you don't have to use the best model. So let me give you the example of Llama 2. When you download the model and you want to run it yourself, you need an A100 GPU with about 80 gigs of video memory for the 70B parameter model. 70 billion parameters, it's a very large model. You can quantize it, you can do 4-bit quantization, and you can make it run with smaller video memory requirements. But a better option might be for you to use a fine-tuned 13 billion parameter model. It's not as good, but you fine-tune it, and it's much faster. So typically you can fit about 5 of those models on the same GPU. So it's 5 times faster. Because if you've actually paid $20K a month for your own dedicated GPU instance, you'll know that it can only handle 1 request at a time. So everybody else is queuing for that request. It's a very expensive operation. So using a smaller model, you're going to fit 5 of those models. So you can only now run 5 of these requests in parallel. It's an important, let's say, method of getting better performance. Now, a couple of other things I would suggest as you start building your applications is to also think about how you're going to deploy your application. Are you going to deploy it on a VM, microservices, Kubernetes? How are you going to scale it? How are you going to manage it in production? So for some of these Python applications, you want to package it. You want to run it usually on a container. You want to make sure the application communicates asynchronously via REST API so it can scale. And the way that you're accessing that large language model has a fallback. What happens if the model is unavailable? What happens if the quality of the response is not good? How are you evaluating the quality of the response? So there are a couple of metrics, Blue Score and Rouge, for example, that you can use to evaluate the quality of a summarization. And if the quality is too low, you might have something in your code that says, I'm going to try another model or a more expensive call, or I'm going to come back with a response, pre-canned response, saying, sorry, I couldn't generate an accurate response to your question. Try rephrasing your question. The worst thing you can do is nothing, because then the model will come up with an answer, which will usually not be what you're looking for. Sometimes it can even be offensive, depending on the question that you're asking. So these are some of the tips and tricks of building AI applications at scale. If there's anything that you can take out of this talk today, is that a modem from 1995 is hundreds of times faster than the fastest large language model today. Work around these limitations. Don't worry yet about AI taking over your job. It doesn't think, it doesn't act on its own, it can't access the internet. It's literally a function that predicts the next word in a sentence, but it does so quite well. Thank you all. And if you follow my YouTube channel somewhere in there, you can find more videos on AI and LLM.
I was just going to say, is it really a tech conference without technical difficulties? I mean, let's be honest. So as he said, you will find his slides, and apologies about that. It's at that time of the day where we need to juice up back on our coffees and our teas. First thing I will say, though, is if anybody is looking for the bathrooms, they're located on my left-hand side, your right-hand side, over on that side. Both men's and women's toilets are both on that side. So for those of you also with any mobility issues, please start making your way towards the back to grab a coffee and tea. So we have lovely pastries at the back, so we will be reconvening in 15 minutes. And don't forget, if you're going out on a stroll, make sure to visit Becky at the desk to get your raffles and be in with a chance of winning some of our amazing prizes today. Thanks, guys.